Okay, hello. So this is today's question, probability question I did. So it's question 8. In part A, we're asked, a fair six-sided die is painted with three sides red, two sides blue, and one side green. The die is rolled three times. Calculate the probability that the three different colors come up. Okay, so I'll kind of walk you through what I did, and then later on, we're going to look at the sample solution I used Gemini to generate. So essentially, if we want to get like all three colors RGB in some kind of permutation, then it means that we must have picked one red, one blue, one green. So that means we have three choices for the red, two choices for the blue, and one choice for the green. And since the order doesn't matter in which we get it, then we have three factorial ways of rearranging. And in terms of the three rows, we could have for each row we would have six choices. So then we would have six choose three, six to the third power. So then hence we would have 1/6 when we simplify this equation. So that's part I. To write this up a bit more formally, like how the answer did it, is that you write P of red is equal to 1/2, P of blue is equal to 1/3, P of green is equal to this. And then to write this, to get different rows, you must row one in the specific order. Then it would be 1/2 times 1/3 times 1/6. Since it doesn't matter, it's 3 factorial, so then it's times that gets the same thing. I think it's the same idea, except they just wrote out with more steps than I did. Okay, part two. The die is rolled three times. Let A be the event the same color comes up every time, and let B be the event that red comes up every time. Compute the conditional probability that P of B given A. Okay, so for this, it's just classic conditional probability. Same color. I kind of did it this way, where I kind of defined A to be the same color, B is all red. So P given A. So then by conditional probability, I have this. And since B and A, like when B is satisfied, A is definitely satisfied. So then P, B, and A is just P of B. So then essentially what I'm trying to find is P of B divided by P of A. P of B is, if it's all red, then each time I have 1/2 chance of getting that. And I have three rows, so it would be 1/2 to the third. And then for each of them, I'm trying to get one color. It doesn't matter what color I get. So I could either have red, all reds, all blues, all greens. So then it's just their probability to the third plus together three of them, right? So then I would just simplify it, and I got that my answer is three over four, 3/4. I guess the answer key did something similar, except yeah, they just calculated P of A and B, I think. For this, yeah, basically they got the same and we arrived at the same. So the method was exactly the same for ours. For part three, the die is rolled n times. Let x be the number of different colors that come up. Show that E of x is equal to this thing. Okay, so how I did this question was that I kind of just thought of x as the number of colors, right? I want to show that. If I know that at n equal to 0, my x has to be 0 because I have no colors. When n is equal to 1, I must have had one of the colors. So there would be 1. When n is equal to 2, it would be somewhere between 1 and 2 because I would have 1 and I would have sometimes 2, so it would be somewhere in the middle. So then my expected number of the thing would just be the maximum of the colors I could get, which is 3, minus the expected of having no green, expected of having no reds or blues of each one, right? So I have 3 colors in total, so that's 3. And then for the expected no green, I would have each one I don't get green. All 3 rows I don't get green. It would be 1 minus 1 over 6 to the n, right? Because for every row I don't get it. And it's the same logic for no blue. I just do 1 minus 2 over 6. And then for the red, it would be 1 minus 3 over 6. And I just simplify it into each one and I get my expected value of what I need to show. I think the answer key kind of did it a little better, like more formal, I'd say, with indicators. So it shows that like there's an indicator for each of the colors, right? And the indicator is red, like 1 if it shows the color shows up, and 0 if it doesn't. So by linearity of expectation, expected value of x is equal to each of the values of the indicators, expected value of the indicators, right? And then the expected value of the indicator would just be 1 minus the probability that it doesn't show up. So then After this, it would be the exact same thing as what I have, except it would just be 1 plus 1 plus 1. I just grouped this together to be my max, and then this one would just be the thing that it doesn't appear. So it's essentially the same thing, except they just included the indicator, which is a nice inclusion to have. Okay, moving on, part B. For real numbers C and alpha, let f of this be defined by this probability density function. Okay, so if it's smaller than or equal to 1, we have nothing. And if it's that, it's this thing. Part 1. For which values of alpha does there exist a value of C such that this thing is a probability density? Give the appropriate value of C for each such A. Okay, so the idea behind this is that if we have a probability density function, then all of the values inside here, the density has to be greater than or equal to 0, right? And also the if we integrate the area under the curve, it should sum to 1. I think that's the two properties that we're kind of going to work with. So this is what I did. I obviously first set to the 1 because I think that would give more conditions, more restrictions. So that's what I did. So I just integrated this from 1 to infinity because it's here over 1. So then I just integrated that. And then from there, I saw that when I put in the infinity, this part goes to 0. And then when I put in 1, this is what I have. Then I just kind of did some algebraic simplification, and I got that C is equal to this thing. And then next, I use my condition of the PDF that it has always to be greater than or equal to 0 at all times. So now I just put in this greater than or equal to 0. So then I got x over x times c has to be greater than or equal to 1 for all x greater than 1. So then my c is greater than this, so c has to be greater than or equal to 1. And I stopped here because I thought I was done. But apparently what I have to do is I also have to find the boundaries for A, right? So over here in the answer key, when I'm gonna go through it, is that they did the exact same work. They just kind of, this is what I was talking about. The area integrates to 1, and then each of them is non-negative for this. So then they integrated this, did exactly what I did over here, and got to this. I also got to this. And then they also got to this, which means C is greater than or equal to 1. This is a step that I did up to this point. But then what they need to do, one more step, is that we need to substitute the value of C back into this equation, right? The alpha is greater than or equal to 1. So then we arrange it and we see that this actually is like basically like the golden ratio. Because when we do this, we get two roots, right? Either the plus or the minus square root 5. And since we know that alpha has to be greater than 1, the condition becomes this. So basically, the condition that I was missing that I forgot to do was actually substituting it back and getting this kind of condition on alpha, which I didn't do. But other than that, I think the strategy behind using these two equations and just kind of finding what C and A are in terms of each other is done well. Okay, moving on to part 2. Um, for alpha equal to 3, let x be a random variable with density of this. For the appropriate value of c, compute this probability x is smaller than or equal to 2 and expected value of x. Okay, so we're given this is the condition. So we first, if we're given alpha equal to 3, then we can find what c is, and then we plug that in, and then we find where that takes us, right? So in my work, what I did was I know that alpha is equal to 3, so then I put it back and I got what my C is. I just plugged in this directly into this equation. I got C was equal to 8/3. So then next what I want to find is the P smaller than or X smaller than or equal to 2. So then it would just be summing up the probability from 1 to 2 of this PDF, right? This is a definition of the CDF. This is just taking advantage of CDF. And I just integrate it and I get this. Then I just do some simplification and I get to that. My answer is 7/24. Next, I'm trying to find the expected value. For expected value, what I do is the same equation, x times f of x. Before it was just f of x. Now, because it's the expected value, I have x. And then because I know it's greater than 1, x is greater than 1, so now I'm summing it from 1 to infinity. And then I just plug back this in, solve this integration, do it over here. I get this. then I get my expected value is this value. I think overall, like in the end, I think like my solution was matching this because it's just normal calculation. There's not much to it. You kind of just do the work. Okay, I guess that ends it off here. Basically, the idea behind this question was that you kind of just tested on whether or not you can work with conditional probability, if you know the complementary, um, or if you know indicator, it would be a lot easier. And then for part B, it was mainly just testing, can you kind of, do you know the PDF? Do you know the CDF? Can you kind of work around that? But I'd say the only part that I really missed was in part I of like forgetting to plug back, finding the conditional alpha. Because I got satisfied the minute I got C. I was like, oh, CNA is this, great. I kind of just stopped there. But really, I should have plugged it back in and continue finding what alpha the condition was. Cool, let's end off here.